let's start the class. Okay. Hi guys, welcome to NEET World Institute and NEET World YouTube channel. Yes, so today's session is for class 12th IPE guys, right? So in this session we are going to concentrate on the short answer questions, that is wave optics. Okay, so let's go into the topic now, right? Yeah. So can we start the topic now? Okay, let's go into the topic. So yes, today's topic is wave optics and this is from class 12 and it is short answer questions we are discussing. Okay, so the first question which we are going to see is explain Doppler effect in light. Doppler effect in light. Distinguish between red shift and blue shift. What is the red shift and what is the blue shift? Okay, so this red shift and blue shift somewhere we have heard, no? Yes, like the VIBGR, like red shift, blue shift, I mean red color, blue color, right? No? Yes. Let's discuss Doppler effect first. So Doppler effect in light. To an observer on the earth, the light from a star moving towards him appears with high frequency or less wavelength. Okay, so from here we can say that the thing is frequency and wavelength are inversely proportional to each other, right? Yeah. So to an observer on the earth, in the light from star moving towards him, okay, appears with high frequency or less wavelength. Okay. Similarly, the apparent wavelength is high in the case of star moving away from him. So when it is moving towards, no, like moving towards him, wavelength will be less. When moving away from him, wavelength will be more. Okay. This changes in apparent frequency or wavelength of light due to relative motion of the object or source is called as Doppler effect. Okay. Because of this relative motion we are considering, no, so that effect is called as Doppler effect, we will say. Okay, so once again we will see what is the thing. To an observer on the earth, the light from the star moving towards him appears with high frequency or less wavelength. Here what happens, away from him in the sense less frequency and more wavelength. Okay, so we will write a short thing, away and towards. So for towards, if we see, wavelength will be towards, no, wavelength will be less, frequency will be more, right? No, so away wavelength will be high, frequency will be less. Keep remember this point. Okay, so if you keep remember these 2 points, and the third point what I should do, the third point is relative motion we should mention. The thing is, this change in apparent frequency or wavelength of light due to relative motion of the source is called as Doppler effect. Okay, clear now? So Doppler effect. So Doppler shift is given by delta V by V will be equals to V radical by C. Okay, this is Doppler shift. Yeah, you can take a note of this. Done? Okay. See, now where v radical is the component of the source velocity along the line joining observer and the source, and c is the velocity of light, the speed of light. Okay. So, v radical is positive when source is moving away from the observer. When it is negative means it is towards the observer. So, away from the observer in the sense v radical, velocity of the radical will be, yes, it is positive. When it is towards in the sense it is negative. Okay. So, this is about the first part of the equation. Can we go for the second part of the equation now? That is red shift and blue shift I need to write down right now. So, when a light source is moving away, okay, from an observer with velocity v, let me take a pen, yeah, yes. So, when a light source is moving away from the observer with velocity v, the apparent frequency observed by the observer is less than the frequency emitted by the source. Okay, the apparent frequency observed by the observer is less. Okay. So, when I talk about the red shift like this, obviously the opposite of that will be blue shift, will go for that also. So, observer is less than the frequency emitted by the source, or the apparent wavelength increases. If frequency is less means obviously wavelength will be more. The shift towards the red end of the spectrum, that is the shift towards the red end of the spectrum. Okay. So, blue shift, if you see, when a light source is approaching here away no, it is going away from the source. If I talk right now, it is approaching, coming towards an observer with a relative velocity v, then the apparent frequency observed by the observer is more. Here it is less, here it is more than the frequency emitted by the source, or the apparent wavelength decreases, that is the shift towards the blue end of the spectrum. So, wavelength is decreased, here wavelength is increased. Here wavelength increases means frequency decreases, here wavelength decreases means frequency increases, right now. So, whatever this thing we have seen in the Doppler effect, that we need to correlate with red shift and blue shift. Okay. You can take a note of this. Can we go for the next one? Okay. So, the next question will be, second question, derive the expression for the intensity at a point where interference of light occurs. Arrive the condition for maximum and zero intensity. Okay. Okay. So, this will be my diagram, like S1 and S2, that slits between them, the distance will be d, we will consider, and let me take the points first. Let us consider two slits, S1 and S2, separated by the distance d. O is the midpoint of between two slits. Okay. We have taken the slits S1, S2, and distance between them is d, right. So, consider a point P on the screen. Okay, this is my screen, right. So, this is slit 1, this is slit 2, and distance between them is d. The midpoint I need to take it as O. If you see here, this is my midpoint, I have taken as O. This is O and this is also O, right now, and I have taken a point P on the screen. The wavelength, the wave from S1 and S2 have the same wavelength lambda and are in the same phase. The path difference between the distance gamma is called as path difference. Okay. Let the corresponding phase difference be phi, right. So, the path difference between the distance gamma is called as path difference. Right now, if you see here, I need to take it as, consider a point P on the screen, the wavelength S1, S2 we have considered, and the path difference, the difference between the path is called as path difference, and its corresponding phase difference is called phi. Okay. Yes. So this is the diagram. So this is the distance between the slits we have taken and the screen. Okay, that is capital D. And when slit 1 and slit 2 are separated by small d distance, and O is the midpoint of the slit 1, slit 2. Okay, where it goes with the same wavelength lambda with same phase, and which is the point P on the screen. So the equation will be y will be equals to a sin omega t for first one, slit 1, right now. Then what about slit 2? It is y2 will be equals to a sin of omega t plus phi. Okay. So now the resultant will be sum of both of them, no? So sum of both of them in the sense, yeah, let me take up and wait. Yeah. So y1 plus y2 I should consider right now. So what happens here? Y1 plus y2, a sin omega t plus a sin of omega t plus phi, right now. So this one we can expand the thing, right. So sin of a plus b, which is nothing but sin a cos b plus cos a sin b, right now. So sin of a plus b, which is nothing but sin a cos b plus cos a sin b, that's it. So I have expanded the thing. So a sin omega t was there as it is. Now a of sin omega t cos phi plus cos omega t sin phi, right. So now what we can do here is we can expand the thing here. So I can say that it is a sin omega t plus a sin omega t cos phi plus a cos omega t sin phi, right now. So from this we have taken a sin omega t commonly outside, which is nothing but 1 plus cos phi. I can write here, this is a sin omega t commonly I have taken outside, it is 1 plus cos phi plus a sin phi cos omega t, right now we have got the equation, right. So a of 1 plus cos phi is nothing but r cos alpha we have taken, okay. So a sin we have taken as r sin alpha. So when this thing are substituted in the equation 1, okay, a of 1 plus cos phi and a sin phi as taken as r cos alpha, r sin alpha, right. So what happens here when we are substituting this? Y is equals to r sin omega t plus phi, where r is the resultant amplitude due to wave at P, okay. So now if we square the things, r square will be equals to a square of 1 plus cos phi whole square plus sin square phi, right. So what happens here? So this is 1 plus cos phi, no, cos phi the whole square. If we expand that, yeah, let me write here. Yes. So if you see here, this a plus b the whole square, which is nothing but a square plus b square plus 2ab, right. So it is 1 plus cos phi the whole square, which is nothing but 1 square plus cos phi square plus 2 cos phi, again plus sin is there, no. So up to this we got the value plus sin square phi is there, plus sin square phi, and these two if I add I will get 1, right, no. So 1 plus 1 is 2 plus 2 cos phi, 2 plus 2 cos phi we will get, right, 2 plus 2 cos phi. So I can rewrite this as 4a square cos square phi by 2, okay. So finally we will get, this is r square, this also square, like what I can do is 2a cos phi by 2 the whole square will be equals to r square, 2 will get cancelled, square. So r will be 2a cos phi by 2, okay. And since intensity is directly proportional to r square, then I will be equals to 4a square cos square phi by 2. So condition is for maximum intensity constructive interference, that is phi is equals to 0, 2 pi, 4 pi, and it goes on. And for 0 intensity it is destructive interference, pi, 3 pi, 5 pi, 7 pi, it odd number will come, okay. So this is the conditions. Yeah, you can take a note of this. Done? Can you go for the next one? Yeah, the next, you can take a note of this first. We'll go for the next question. Okay, the last one first. Done? So, the condition is there. Take it first. Okay, done. Okay, so third question is, does the principle of conservation of energy hold for interference and diffraction phenomena? Explain briefly. Yes, the principle of conservation of energy holds good for phenomena of interference and diffraction. Yes, obviously yes. Okay, the first point. Second point, what we should write is, in interference, the energy that disappears at dark bands reappears at bright bands. Okay. In interference, what happens? The energy disappears at dark bands, reappears at bright bands. Energy is only redistributed, not lost. It has not lost. Yes, no. Like whatever it disappears here, it has been appears in the bright one, right? So thus total energy remains constant, satisfying conservation of energy. Like fourth point is, similarly in diffraction, energy from dark region is redistributed into bright regions, which means again conservation of energy only, right? So hence the principle of conservation of energy holds good for the both interference and diffraction phenomena. Okay, this is the answer for the third question. So simple thing, whatever have been lost in the dark band reappears in the bright band, right? No, that's the thing in interference. Similarly, if you see, energy from dark region is redistributed into bright region. Okay, here redistributed, here it disappears and reappears there. So this is interference and this is diffraction. Okay, so both holds the conservation of energy. Okay, so energy has not been lost there, it has been distributed or again reappears there. Okay, this is the thing. Okay, we'll go for the next question. Okay, how do you determine the resolving power of your eye? So you can estimate the resolving power of your eye with a simple experiment, by doing simple experiment. See, prepare black strips, okay, width of 5 millimeter, separated by white strips of increasing width of 0.5 millimeter, 1 millimeter, 1.5 millimeter, 2 millimeter and goes on. Okay. So paste the pattern on the wall at eye level. Okay, we should paste the pattern in the wall in the eye level. Eye level in the sense like straight. Okay, that's the thing. So view the pattern with one eye. So move closer or further until two adjacent black strips just begin to merge the smallest visible white gap, correspond to the resolution limit. Okay. So what is the thing they are asking? Determine the resolving power of your eyes. So what is the step I need to involve there? That's it. If you mention those steps, that's more than enough for this question. So simply you can mention the first point as taking the black strips of width 5 millimeter separated by white strips of increasing width, which is 0.5, 1, 1.5, 2, 2.5 and goes on. Okay. So paste this pattern on the wall and the eye level, view the pattern with one eye. Next, last point is move closer or further until two adjacent black strips just begin to merge. Okay, just begin to merge. The smallest visible gap correspond to the resolution limit. So let D will be the width of the white strips, just resolvable. D, capital D is the distance between the eye and the pattern. So resolving power will be small d by capital D. Okay, this is how we will do. So what is the thing? Once again you see, prepare black strips and white strips. Okay, so black strips is width 5 millimeter, white strips I should increase like 0.5, 1, 1.5 like this. So I should draw like this, like the parallel manner. Okay, black, white, black, white, black, white, like that. Okay, that's the thing. So this is the answer for this fourth question. Done? Can we go for the next question? Okay. So next question is, explain the polarization of light by reflection and arrive Brewster's law from it. Okay. So when unpolarized light is incident on a plain glass plate, it's partially reflected and partially refracted. The thing is, when unpolarized light is incident on a plain glass plate, so partially will be get reflected and partially will get refracted also. So at a particular angle of incident called Brewster's angle, okay, that is IB we will mention. The reflected and refracted rays are perpendicular to each other and reflected ray is completely plane polarized. Okay, so what we can say is at particular angle of incident called Brewster's angle will say, and the reflected and refracted ray are perpendicular to each other and reflected ray is completely plane polarized. So for Snell's law we know that mu is equals to sin I by sin R, right? So sin, like since I plus R will be perpendicular, now it's equals to 90 degree, right? So sin I by cos I will be equals to tan I. So if you see the diagram here, it's unpolarized light incident on the plane and some are get reflected and some get refracted also. Okay, so if you see here, this two thing is perpendicular to each other, like reflected and refracted. Okay, that's why we have taken like IB plus R, like Brewster's angle plus refracted angle will be equals to 90 degree. Okay, so this is known as Brewster's law. Hence the tangent Brewster's angle equal to the refractive index of the medium. Okay, this is about the fifth question. Okay, so then now we will go for the next question, that is the last question of this class. Yes. Discuss the intensity of transmitted light when polarized sheet is rotated between two crossed polaroid. Okay, So if you see here, we have taken a sheet, we have shifting the angles, like first I have taken, then parallel, then we have taken to angle, again totally perpendicular to the plane. Okay. So if you see here, let I naught be the intensity of polarized light after passing through the first polaroid P1. After passing through second polaroid P2, rotated by an angle theta. So after passing to second one, we have rotated to angle theta, right. Now the light emerging from P2 passes through third polaroid P3 crossed with P1. Crossed with in the sense, whatever P1 was there, it's exactly perpendicular. Okay, the intensity of light emerging from P3 will be, so P1 to P2 will be I naught cos square phi, so cos square theta. Okay, I naught cos square theta. When we are taking to P1 and P3, no, when I am considering, it is I naught cos square theta into cos square pi by 2 minus theta. Okay, so what happens here? So I need to expand the things. Now I equals to I naught cos square theta sin square theta, which is nothing but I naught by 4 sin square 2 theta. Okay, so therefore the transmitted intensity is maximum when theta is equals to pi by 4. What is pi by 4? Angle. It is 180 by 4, right? So what will be the angle? So it is 180 by 4, so 2 times it is 90, so 45 degree. So exactly 45 degree, it is maximum, right? Okay, so that's the thing. So this is the answer for the last question of the class, right? You can take a note of this. Done. So it is maximum at theta is equal to 45 degree, or you can mention it is pi by 4. Okay. So with this we'll end our session of today's class, that is wave optics of class 12th IPE, that is short answer question. Okay. So we will come with the next lesson of short answer question in 12th, okay, in the next classes. Okay. Bye guys, we'll meet in the next class.